So in this presentation, I'm going to clarify a few points on your A2-2 organic notes, specifically on the amides. The top part of the page lists off the specification, and there's really only one new reaction in this, and that is the dehydration of the amides. So you'll see the definition from our CA document, and that should be embedded in the notes. We look at these as a homologous series, so we've come across amides before as having a C double bond O NH2 group, so methanamide would be where they've just simply got that group and therefore need a hydrogen, so structure would look like that, C double bond O NH2 with the hydrogen in place. Skeletal representation would be as shown. You could go down and complete that, and I'll go through very quickly some of the structures there. So ethanamide would be the same with C double bond O and NH2, but then one extra carbon. Skeletal representation is shown. Propanamide, 3 carbons. Skeletal representation, and so on down. Butanamide, and simply adding one more stick onto the skeletal representation. Pentanamide and hexanamide. So again, keep counting. That's the first one. So if it's hexanamide, you do that as the amide group, and then 1, 2, 3, 4, 5, 6 to give the extra one. The structure at the bottom, if you've tried that one, the pentanamide is basically the same as this, but the additional bit, the 4 hydroxyamines in the 4th carbon, there's no H. So there's our 1, 2, 3, 4, 5 carbons, and then the 4th carbon there, that being the first one, this being the 4th one, has got the OH. The properties of these, they tend to be solids, which means high melting and boiling points. And you remember that because they're molecules, intermolecular forces would explain this. All molecules have van der Waals forces between them, but what really accounts for it is the fact that they can form relatively strong hydrogen bonds. And if in the exam you're asked to do this, don't forget to include the van der Waals forces, but then talk about how the hydrogen bond arises. And the hydrogen bond arises, remember, the attraction of the lone pair of electrons, an electronegative atom like oxygen, fluorine, or nitrogen. So there's that lone pair of electrons on the oxygen, and it's attracted to the hydrogen on a neighboring molecule. So in this case, it's another amide, and this hydrogen itself has to be attached to the electronegative nitrogen to give it the delta plus. That means that the hydrogen bond is that strong attraction. And you can read over and see where the hydrogen bonds arise between them. It means that most amides have got very, very strong hydrogen bonds between molecules, and in fact many even form dimers, which accounts for the relatively high melting point. To prepare amides, 2 ways of doing it. One is to take an ammonium salt off a carboxylic acid and dehydrate it. Now you have to form the ammonium salt in the first place, usually by reacting the the corresponding carboxylic acid with something like ammonium carbonate or ammonia itself. So the first one I'll go through is it reacting with ammonium carbonate, and then once I've finished that, you can try the example that's a bit further down in your page there, where you're reacting it with ammonia. So the ammonium salt of the carboxylic acid, so we're going to try and form propanamide. So we start with propanoic acid, 3 carbons, ammonium carbonate, NH4 2CO3. So we need 2 propanoic acid. The salt, so we'll replace that H with an ammonium group. So then it'll become the ammonium propanoate. So there's the name of it, ammonium propanoate. And then because it's acid plus carbonate, salt, water, and carbon dioxide. Now, it's this ammonium propanoate that's dehydrated, so there I've just drawn the structure of the ammonium propanoate again, and dehydration is the removal of those 2 hydrogens and an oxygen, and then that gives us the amide group. And then this amide, 1, 2, 3 carbons, so it's going to be propanamide. So you try the example underneath with ammonia. The solution to this is then, this time we've got 3-methyl butanoic acid, so 4 carbons. So 1, 2, 3, 4. On the 3rd carbon, this one, you'll have a methyl group and ammonia. And again, you may have drawn the structure out, but that's fine. And then what you'll get is the ammonium salt. Now, it's the ammonium salt of 3-methyl butanoic acid, so 3-methyl butanoate, so ammonium 3-methyl butanoate. To dehydrate it, again, we've just drawn that structure down here. So that's the structure of the ammonium 3-methyl butanoate. And when it dehydrates, it loses 2 of those hydrogens, that oxygen. So that has become the amide. And then the name of the amide based on 1, 2, 3, 4, so butanamide, but on the 1, 2, 3 carbon, there's a methyl group, so 3-methyl butanamide. The other preparation that you might be asked is the preparation of an N-substituted amide, and those are made by reacting the corresponding amine with ethanoyl chloride being the acyl chloride that your specification asks you. So for example, ethanoyl chloride with ethylamine, it would be shown here. So you can see there's our ethanoyl chloride, there's ethylamine. When they react together, we lose our chlorine from here, our hydrogen from there, and then those link together. It's based on an amide, so in this case ethanamide, and then this one has an ethyl group on the nitrogen, so N-ethyl ethanamide. And don't forget when you're doing the equation to include the hydrogen chloride to make sure it's balanced. So you could try propylamine with ethanoyl chloride, and again pause it, and then I'll show the solution in a second. So propylamine's like that, ethanoyl chloride, the N-alkyl ethanamide, and hydrogen chloride, and the name of it then N-ethyl propanamide. The amides are very weak bases. The reason for this is, again, it's to do with the lone pair of electrons in that NH2 group. Now, as we've seen before, the more available they are, the stronger the base. So these are weak bases, so it means that this pair of electrons must be not very available. And if you look at what really makes them less available is beside you've got a C double bond O. Now, the double bond is basically a sigma and a pi bond, so the sigma bond is shown as a line there between the carbon and oxygen. The pi bond is formed by the overlap of 2 p orbitals, and you can see that those p orbitals are in fairly close proximity to the lone pair of electrons on the nitrogen, and basically those electrons all get linked together. Again, the details of the mechanism isn't required at A level, but all that you have to see is that that pair of electrons will get involved with that, making it less available for bonding. So when we look at a scale of basic strength, remember earlier on we had seen this with amines. So ammonia we had sort of put in the middle. Primary amines, because of the positive inductive effect of the alkyl group, that they were stronger bases than ammonia. Secondary, remember, were here, and tertiary even stronger, so the amines tend to be stronger bases. Phenylamine we saw because of the delocalized pi ring of electrons on the benzene ring. It was a weaker base, and the amides are even weaker. Again, that pair of electrons gets more because of the close proximity of the pi bond with the double bond there. It's less available. The lone pair on the amides are less available for reaction, so they tend to be the weakest bases. The reactions of amides, 2 of them. One is the dehydration. Now, the dehydration uses phosphorus 5 oxide. If you wouldn't mind updating your notes, I had earlier on, previous to doing these notes, I had a wee bit more about phosphorus oxide with a previous specification. I must have edited to put P2O5. I should have put the molecular formula, which is P4O10. P2O5 is the empirical formula of phosphorus 5 oxide. So if you'd maybe change that to P4O10. And the idea of the reaction is that to dehydrate amides, you have to heat it with P4O10. Now, P4O10 is a solid. Most amides tend to be solids, so the solid mixture would be mixed together and then put into some sort of container and heated. And what it'll do is it'll dehydrate. Now, dehydration is removing of water. So those 2 hydrogens and this oxygen will be removed. That'll lead to the formation of a nitrile. And the nitrile tends to be liquid. So once it's formed, it can be separated off by simple distillation or fractional distillation. If you're putting an equation, so basically the heating of it, P2O5 is not really part of the reaction as such. It's almost like a catalyst for it, but it helps remove it. And what happens is you put the amide, CH3, CH2, CO, NH2, you'd form the corresponding nitrile. And this one, because that's the first carbon of the nitrile, 1, 2, 3, that's going to be propane nitrile. And water is taken away by the phosphorus 5 oxide. So you could try ethanamide for yourself. and the solution to it there's a thanamide, 2 carbons, you would get the nitrile, and this time, because the nitrile has got 2 carbons, ethane nitrile. And the last reaction is not a new reaction to us. Again, you'd probably have to go back to your A2-1 notes if you haven't seen these for a while. Maybe take a quick revision over these and then try and do this. This is where we can form organic acids. So it was in our carboxylic acids notes, and the formation of those from hydrolysis of amides. And they can be hydrolyzed either by dilute acid or dilute alkali. So have we look over them and then try and write the 2 equations for it. Again, pause the video. I'll go over the solution in a second. So propanamide would be 3 carbons, so CONH2, the amide, and then that's 1, 2, 3 carbons. And when you're heating it with dilute hydrochloric acid, water, and HCl, it gives the corresponding acid. So propanamide would turn into propanoic acid, and then the other product would be an ammonium chloride salt. With the alkaline conditions, you'll get the salt of the acid. So there, for example, is an illustration of sodium hydroxide. So we've asked you for potassium hydroxide. So butanamide, 1, 2, 3, 4, potassium hydroxide. That'll give you the potassium salt of it, and then ammonia given off. So butanamide would turn into potassium butanoate.